So, good morning, my dear students. Today we are going to start our new lecture. The lecture is dedicated to sequential functional chart language. Yes, so this programming language is graphical language. So in this part of our lecture, we try to discuss about basics and features of this language. Expressive power. The SFC language has the visibility of state diagrams and has common features with Petri nets. This is why the SFC is well suited for describing the program's algorithm. A graphical representation of the process. Its second feature of this language. SFC is not the only graphical language of this standard, but unlike the other two languages, it means languages LD and FBD, it allows you to operate at a high level of abstraction. So next feature is possibility of preliminary design. You can start using this language at the earliest stages of the project to describe the intended behavior of the control system in general terms. Next feature is ability to drill down, and the language schema created at an early stage of design can be supplemented and changed as new information becomes available. So, next feature, support for code fragmentation. Using SFC allows you to divide the code into separate blocks that will be executed in different PLC cycles. This way, the maximum cycle time will be reduced. So, we discussed about basics and features of this language, and we are continuing. So, what about syntax of this language? Yes, creating a program in the SFC language includes the following stages. So let's see what stages. Each stage of the process is represented as a step. The step is the main element of this language. Next main element of this language is a transition. Transitions between steps are described using conditions. Operations that must be performed at a particular step are encoded in actions for this step. Each action has a classifier. Action is also one of the main elements of this language. The SFC schema allows you to visualize the process as a sequence of steps and see possible ways to execute the algorithm. So this is very convenient and helps with design, development, and debugging of our program in this language. So let's see the main elements of this language. Steps and transitions. As I said, steps and transitions are basic main elements of this language. The SFC allows you to present a program as a sequence of steps linked by transitions. Each step is characterized by the actions that are being performed, and each transition is characterized by conditions. This step describes one of the stages of the process. At any given time, the step is either active or inactive. Below is a graphical and text representation of the step. So in this picture, we can see the block designation in the program. I meant not block, I meant step. This is the step designation in the program. And also we can see the step description in the program. This is the step. So the step has implicit variables hidden behind the namespace that matches the step name. So this is variable is a flag for step activity. If this variable has a true value, it means that step is active. If variable has a false value, it means that step is inactive. So next, this variable, the time elapsed since the step was activated. It means that if the step is inactive, the variable retains its last value. When the step is activated, the value is reset to this value. It's time type variable. So the initial state of our unit is determined by the values of its variables, as well as a set of initial steps. So it means steps that are active when the programming unit is started. Each SFC schema has only one initial step. In the graphical view, it's marked with a double outline, and in the text view, it's marked with the initial step keyword. When initializing the application, the activity flags for normal steps are set to false, and the activity flags for initial steps are set to true. In this picture, we can see the initial step designation in our program. As I said, this step marked with a double outline. So next element, transition. As I said, it's also main element of this language. A transition is described by a condition that makes the next step active and stops the current step. Transitions graphically connect to the lower part of the previous step and the upper part of the step that follows it. The transition condition is a Boolean expression. Yes, every condition for transition is described by Boolean expressions. So in the graphical view, transitions are represented by vertical lines connecting blocks of steps. The transition condition can be described in one of the STLD or FBD languages. The transition is written in the form of design between the keyword transition and transition. So in this picture we can see the transition designation in the program. This is the transition, how it described in our program, and this is the transitions conditions. So the transition name is local to the program unit where the step is declared. During the transition condition check, no side effects can occur. For example, assigning values to variables. So, next main elements are actions. So each step can have one or more actions associated with it. If a step does not contain actions, the program simply waits for the condition to proceed to the next step to be met. The action has a name and a body implementation that can be encoded in any of the languages of standard. Graphically, the action is represented by a block located to the right of the step and linked to it by a horizontal line. The action name is local to the program unit where the step is declared. The declaration of an action is accompanied by the implicit creation of an instance of the action control function block, which allows you to control the process of its execution. Each action has a classifier that defines how the active step affects the execution of the action. For example, an action with the classifier n will be performed while the associated step is active. The classifiers L, D, SD, DS, and SL require an additional value of the time type to determine the duration of the action. So, next, classifiers of actions. In this part of our lecture, we will talk about classifiers of actions. So, first, classifier is empty classifier. It means that the action is performed while the step is active. Next, N, non-start. The action is performed while the step is active. P, pulse. It means pulse. The action is performed once when a step is activated and deactivated. S, it means start. The action runs until it's reset by the R action. R, it means reset, resets the saved actions. L, time limited. The action is activated along with the step and remains active for the specified time, but no longer than the step. So D, it means delayed. The action is activated after specified time after the step is activated and remains active as long as the step is active. If the step is active for less than the specified time, the action won't be activated. So as the start and delay, the action is activated within the specified time after the step is activated, even if the step is already inactive. However, if you reset the action during the activation delay count, the activation won't occur. The activated action remains active until reset. So next classifier is DS. It means delayed and start. The action is activated after the specified time after the step is activated and remains active until reset. So next, SL, start and time limited. The action is activated along with the step and remains active for the specified time regardless of the step's activity. The action can be deactivated prematurely from another step with the classifier R. So in this part of our lecture we discussed about classifiers of actions. So the SFC schema is processed from the initial step, which becomes active immediately when the program unit is called. Then the activity of steps is distributed through direct links when the corresponding transition conditions are met. The transition becomes active if all the steps preceding it are active. It means steps connected to it by vertical lines. If the transition condition is met, the next step becomes active. So after you complete a transition, the step that preceded become inactive. This process is called cleaning. The cleaning time is quite short, but it can be considered zero. In practice, this time depends on the specific PLC. For the same reason, the activity time of any of the steps cannot be considered zero. If multiple transitions can be cleared at the same time, this must occur within a single PLC cycle. The transition condition must be checked only after the effect of activating the previous steps has spread throughout the entire SFC schema. The next elements of this language are divergence and convergence. Divergence is the relationship between an SFC character, step, or transition and two or more characters of a different general type. So convergence is the relationship between several common type of SFC characters and a different type of character. So divergence and convergence can be alternate or parallel. In this picture, we can see the alternate designation of divergence and convergence in the program. Yes, because it's one basic main part of this language. So, continue. Alternative divergence is the relationship of a single step with multiple transitions. Alternative convergence and divergence are shown in the language using a horizontal line, yes, as we saw in the last picture. Convergence for alternative divergence is the association of multiple transitions with a single step. So next main element is parallel divergence. Yes, this is the relationship of a single transition with multiple steps. When the transition condition is met, the first steps of all parallel branches become active. This approach is used to describe control process operations that are performed simultaneously. Convergence for parallel divergence is the relationship of several steps to a single transition. So in this picture we can see the parallel divergence. This is the designation of this process in the program. So next we can see the process of creating a program unit in the SFC language. To do this, We need to select the appropriate language in the dialog box. Yes, we are selecting the SFC language. In the window that opens, you can see a toolbar that allows you to write a program in the SFC language. It's common view of the program written in SFC language. Yes, we can see in this picture a parallel divergence blocks. Yes, this is the initial step, its action, and this is the steps, and this is the conditions. Yes, to pass to the next step. Yes. So next, the structure of the simplest control algorithm is a set of sequential steps, as shown in the figure. So the initial step, marked with a double outline, automatically starts when the program unit is called for the first time. Yes. Then, as the transition conditions are met, the remaining steps are activated sequentially from the top to the bottom. Yes. In a significant number of cases, we need to perform steps and cycles rather than just one. In this case, you can set a loop, yes, as we see in this picture, but after the last condition is met, the initial step is reactivated and the execution process begins again. So for programs with no infinite loops, we can enter conditions for stopping the loop. In the above diagram, the loop has an output condition. Yes, this is the output condition. As long as condition T21 is met, steps S1 and S2 are sequentially executed in a loop. After this condition, the stop step is switched to, which remains active until the application is restarted. So, parallel processes. As we said, the SFC language allows you to describe processes that run in parallel. This means that at some point in time, two or more steps of the SFC schema will be active. Parts of circuits with parallel branches starts with divergence and ends with convergence. So in this picture below, we can see the parallel processes which it can be written in program. So in this picture we can see the steps with actions. Yes, this is the actions. As we see, every step can contain one or more actions which are connected with every step. So, thus In this lecture, we discussed the main stages of programming in the SFC. Thank you very much.